Right, now let's get into a proper introduction to our topic of chemical reaction engineering. Of course, the reactor is the heart of any chemical process because here we are actually doing the main function of chemical engineering, which is taking some raw materials, typically at a much lower value, and converting it into some higher value species or stream or chemical profile. So that's pretty much core to chemical engineering. Designing this reactor is mainly about managing the reaction rate. So we may have several complications in the reactor, and you've heard about application of catalysts and so on, but it's really all about managing the reaction rate. And you may have multiple reactions going on in the reactor. You'll want to balance the rate at which your primary product is being produced, and you'll want to reduce the amount of byproducts or waste that are formed. So we want to carefully manage our reactor reaction rate and all its competing reactions, and we still want to maintain a high productivity. This is quite different to what the chemists do. So to a chemist, we are typically trying to establish whether or not a reaction occurs at all, and we might be involved in the intrinsic reaction rate, but that's typically happening on a small scale. It might be happening on the order of cubic centimeters. Whereas as chemical engineers, we are typically dealing with volumes around perhaps 50 tons a day. If it's a small plant, 50 tons per day is what we start with. And we are talking about large volumes, hundreds of cubic meters of reactor volume. So those are the scales that we are thinking at. And when operating at such large scales, a whole new host of problems arises. So problems of scale typically involve many higher costs, and what we might think of as being very easy to do in a lab suddenly becomes a whole new level of difficulty when we want to do it on the cubic meter scale or on the hundreds of tons per day scale. So we want to design a reactor, and it's really just a space where we can control things like the temperature and the concentration. We want to design the space so that we achieve the productivity that we want and that we are getting our components out at the composition, at the purity that we've defined. So I've mentioned a bit about the scale here, so tens of cubic meters or hundreds of cubic meters in volume. We should say that there does exist this field of micro reaction engineering. So for the fine chemical sector, you do have very small reactors as well. But in the typical commodities chemicals industry, it's on the order of hundreds of cubic meters. Most reactors do have catalysts that are there to promote the reaction rate. So the catalyst is another chemical which makes it easier for the reaction to proceed. And we look at in some detail the thermodynamics around that and the kinetics and so on. Temperature control is so important to reaction engineering that most reactors in fact look like heat exchangers. And we'll talk a bit more about why temperature is such an important variable in reactors. Here's a simple observation that we find in many systems. The reaction rate is such a strong function of temperature that some reactions, or in fact many reactions, increase by a factor of 2 for every 10-degree rise in the temperature. So think about that. The reaction rate is doubling every time the temperature goes up by just 10 degrees. So that tells you how sensitive the reaction rate in the reactor is to even apparently small changes in temperature. So many reactors are operating in this range, close to ambient, all the way up to about 800 Kelvin. And it's such an important factor that, yes, we said this already, that most reactors look like heat exchangers. Other things that play a role include the hydrodynamics or the flow pattern through the reactor, so the nature of the mixing in the reactor That's another very important aspect, and that in fact strongly influences the way that we go ahead and model that reactor. So the hydrodynamics of flow pattern in effect influences your concentration profile. So as we expect, regions with high concentrations of the reactant, those regions will have a high reactor reaction rate. So here's another picture of what the reactor looks like. Maybe let's look at the one in the scheme first. So here's a typical engineering drawing that's trying to show also where this reactor is sitting in some column or some tower. So here's a floor level, and here's the reactor itself. And you can see we are feeding in the reactants here. There's a strong agitation going on here. And then you've got a vent for some gases here, but the product is overflowing from the reactor there. So that's just a kind of simplified view of what's going on in the reactor. And so here's what that might look like. So as we said, there's a little bit sticking out above the floor level here, and then in the other sections the majority of the reactor is sitting there. And like we said, temperature control is extremely important in reactors. You can see this reactor is jacketed. So if you like, you can imagine a double pipe. So this is a short pipe, and then there's another shorter pipe wrapped around that one, and we've got some coolant flowing around that. So we are relying on cooling on the outside of the reactor to help maintain the temperature there. So that's one type of control. We could be controlling the flow rate of the coolant through this cooling jacket. That is one thing that could help us to maintain the temperature in there. Another kind of control we might be applying is that we want to maintain the level here. So there might be a liquid level here. I'm not sure if you can see this color, but there's a pale green color here. And then in the space above that, that's in principle a gas phase. So we have a liquid level here, and we might be controlling the flow rate through this reactor. So we've got flows in and flow out here. So we might be controlling those flow rates such that we maintain the level at that value. So there's a whole control system, and of course there are other courses later in the degree that cover things like process dynamics and control. That's literally the name of the course. So in that course you will learn in detail about how you construct such control systems. In this course, we'll just treat that as an in-principle thing, so we can focus on the actual design of the reactor. Right, so temperature is important, level is important, composition in the reacting space is also important. So we'll be looking at all those in detail. Here's another one that shows us the internals, and this is one where we have a catalytic reactor. Like I mentioned before, temperature control is so important in our reactors that they look like heat exchangers. And if you look at this, you'll recognize this as a kind of shell and tube heat exchanger. So you might be sending in some cooling fluid here. So this coolant is flowing around the outside of these thin yellow-colored tubes. So you've got perhaps a coolant flowing through here, and then you've got your reacting fluid that's entering the tubes. So obviously there's some kind of manifold here that helps you transfer from here into the tubes. But you've got your reacting fluid in the tubes, not in contact with the coolant fluid. And then there'll be some exit somewhere to remove the product. So your reacting fluid is passing through these tubes, but in contrast to a shell and tube heat exchanger, your tubes may be packed with these particles, which might be catalytic particles. So there might be solid particles impregnated with some kind of chemical which promotes the reaction rate. So we'll be looking in detail at designing those catalytic particles and those catalyst reaction rates and so on. So that's just a picture to help us understand how reactors can so easily start looking like heat exchangers, and about contacting with catalytic particles and so on. In terms of the reaction rate, So we typically define the reaction rate like this. So this is, in a sense, the default units of the reaction rate. So moles per second per cubic meter of reactor space. So let's just read it here. The reaction rate is a rate at which it's saying the reactant feed is converted to the product feed, but we'll see we abstract this a bit more. So we accept that there's going to be some rate at which we are converting the reactant material into product material. And when we use this term rate from perhaps the way that we are used to speaking, some of us sometimes use rate interchangeably with speed. And it's important to get this distinction right? If you mix up rate and speed, that can lead to errors. So we want to be careful always to renew our understanding of rate. You'll find in chemical engineering, the better you understand this concept of rate, the easier it becomes to understand much more complex concepts. So right now we'll just say the rate is the frequency at which you are translating one type of chemical component into another, and that rate is given to us on a basis of time passed and reaction space occupied. So the rate is the quantity of some component that's reacting on a basis of time passed and reaction space occupied. So like we said, the amount is moles in this case, and then per time passed, so per second in this case, and then per reaction space occupied, so per cubic meter. So that's kind of abstractly, kind of generally defining our reaction rate. And we will revisit this. Sometimes the reaction space occupied is not a volume of reactor. Sometimes the space can even be the surface area of a particle, or it might be something like given to us on a per kilogram of particles. So this changes quite a lot, but most of the time it's moles per second. So that's really what we want to get to. We want to know how fast are we producing a product in our reactor. So anyway, Ri, we say generally, is the rate of formation. So that's the default definition for Ri. It's a rate of formation. And you can define a rate of consumption, so that's not what this is. Ri is the rate of formation, the rate at which our component I is appearing. Okay, so what are the things that dictate Ri? How do we find a number for Ri? How do we know how quickly our component is appearing or disappearing? So first off, of course, the kinetics of the process. So there's some reaction that we are interested in. So there's some chemical rate, or not rate, some chemical equation that applies, and it's telling us perhaps A and B are combining and giving us C. So what's the tendency for that to happen? How much affinity does component A have for component B? Do they easily combine to give us C, in which case it will happen many times, and so we can talk about a high reaction rate? Or are there certain barriers to A conjoining with B to give us C? So the kinetics, that tells us how the species tend to react, and hence the rate. And that is a strong function of temperature. So the rate at which the actual chemical reaction occurs, that, as we said many times now, that is a strong function of the temperature. So that's one. And then the other thing is the concentration of the reacting species. So even if A and B have a strong affinity and they want to react, if you don't have enough of either A or B or both, then there just isn't enough contact between them for the reaction to happen. So the concentration of the reacting species, that's the other side of it. That's also what's behind our reaction rate. So kinetics and concentration. And this last part might seem obvious to you, and you're wondering why I'm mentioning it. And that's because the concentration is influenced by a number of things. So number one, mass transfer. How fast are the species moving through the reaction space. So even if they are convecting at high speed through the reactor, so even if we are pumping them through the reactor fast, they might not actually be in close contact because there might be some rate of delay in A contacting with B. So for example, if A and B react quite fast, then actually C, the product, might form and somehow retard the contact between A and B. So there are various factors that influence mass transfer. So we'll talk about those in some detail in the course. Then, of course, the hydrodynamics. So how does your convective flow distribute itself through the reactor? So going back here to this picture, if A and B are, let's say they are traveling down one of these tubes and they get consumed at some point, then of course we have a high concentration of the product C coming through here, which is a good thing. But then it also means that all this tube is basically wasted space. We aren't reacting anymore A and B, and hence this reactor can tolerate a higher flow through. So chemical engineering is not just about can this reaction happen or even what's the rate and we're done. It's a careful balance of the flow through a system. We want to know how fast are things flowing through the system, then how are the molecules diffusing through the particles, and how are they contacting us? So what's the rate? The rate is varying across. The rate is not one thing. You can't say, yeah, I measured the rate here and it was 50 moles per second per cubic meter, and that's the rate in the whole reactor. So the rate might be changing a lot down the tube. So the rate might be 50 up here, but because the components get converted, then by the time we're looking down here, we might have even a zero reaction rate. So estimating the reaction rate is not such a straightforward thing. Even in a simple case like this, we can see the reaction rate might be varying down this tube significantly, and that can complicate our efforts to predict the reaction rate and hence design this reactor. So the rate here, we can define it. We can say, yes, we think this is an important thing to know, that these are the number of moles being converted per second per cubic meter. But we don't know how true this stays over the entire space of the reactor. So this itself might be a function of other variables in the system. So that's partly because the concentration might be different in different places across the reactor. It might also be because the temperature is also different across that reactor. And in fact, in this picture, it's deliberately drawn to show that as the cooling medium is flowing over the tubes, it's heating up. And so it comes out warmer than it came in at. And then that implies to you here also that you're coming in perhaps at a high temperature and the temperature is dropping through here. So the reaction rate is varying, number one, because of the concentration varying, but the reaction rate may also be varying because the temperature is dropping down the tube here. So there are all these influences at play, and we are expected still to be able to design this reactor. And it's still possible. So we'll work through the material and energy balances, and we'll show we can indeed we can design this reactor, and we can design it exactly. We can design it exactly right, and that's because we have all this wonderful theory that helps us do that. So here, temperature, these are the influences. Yeah, the reaction itself, that's consuming and producing the product. So the concentration is varying across the space because of things like mass transfer and hydrodynamics, but it's also varying because the reaction itself is happening, because the reaction is consuming your reactants and it's giving off products. So the reaction itself is impacting on the concentration profile. So those are all the things we have to think about, right? When we look at this, it looks nice and innocent, but there are many, many things behind this reaction rate, and we have to design around it. Now, when you hear all this, it should occur to you, and I'm hoping it's occurring to you, that, well, I've got my trusty Navier-Stokes equations. I can always go and and create a simulation which shows me I can solve my partial differential equations across the entire reactor volume. I can cut this reactor into tiny differential elements, and I can write balances on every single element, and I can solve for the profile of temperature and concentration. I can solve for every possible variable at every possible point inside this reactor space. And yes, it's true, you can use Navier-Stokes equations to solve for the concentration profile and the temperature throughout the reactor. Now that's true, but it's brute force, right? It's like taking a machine gun to kill something that you could get away with just with a breath of air. You could get rid of that problem. So it's not the case that you need to go to such a high level of detail to solve these reactors. And that's because there have been some very clever chemical engineers over the previous decades. It was partly because they were so clever, and partly because it was out of necessity that modern computers were not as accessible back then. So, I mean, today you can just go ahead and download some CFD software and do all this. But back then you had to use your brain, right? Back then you had to figure out a cleverer way of figuring out the reaction rate and estimating what kind of product was coming out here. So these are some of the approaches that we learned then. We learned that there are some ideal reactor types: batch, plug, mixed flow. So we'll be using these ideal types to produce extremely simple models of the reactor. So instead of dealing with the partial differential equations and so on, we'll actually be able to model reactors like these with simple algebraic equations that you can solve with a pencil and piece of paper. So that's a large part of reaction engineering. Having the means to estimate where we can apply approximations, and through those approximations we can get very accurate estimates of how that reactor will perform, even without resorting to these brute force methods. So we'll be dealing with these ideal reactor types next week. So anyway, that was all just my introduction to this field of reaction engineering, and these are the types of reactors and what they look like and so on. Let's now look into reaction kinetics, and again we are going to try to establish the framework behind estimating the reactor reaction rate. Of course, a study of reaction kinetics is helped by revisiting the kinetic theory of gases. So please do have a read through that. That's an important way to start understanding thermodynamics and reaction kinetics. We'll take that as read because that's really related more to the chemistry fundamentals. And here, just revising this concept of temperature once more. We mentioned how important temperature is in general, but we also want to say here that the concept of temperature, we know it's defined as the average kinetic energy of the molecules. So we can think of temperature as telling us how fast the molecules are bouncing around, and clearly the faster the molecules bounce around, the more they collide with one another. And so the higher the temperature, the higher the chance of something colliding and reacting. And so we can say then it's obvious that as we increase the temperature, the reaction rate must rise. So all reaction rates will increase with temperature. Right? And even if we have unwanted reactions along with the desirable primary reaction, we may have unwanted side reactions. And so as we increase the temperature, all rates will increase, but some rates will increase to a greater degree than others. So we have to make sure that the rate that's desirable to us, the reaction that's desirable to us, we'd like that to increase more with temperature. But that's something dictated by nature. We can't really influence that. Well, we can to some extent, which we'll talk about later. Anyway, before we get to all that, let's look at basic reaction stoichiometry. So when we describe the reaction that occurs, we typically do that in the form of our reaction equation. So here, for example, two molecules of A combine and give us one molecule of B. So we want to know the rate at which this happens, and as we said before, we define the rate of formation of component I as Ri, and the default units are moles per second per cubic meter. This is per cubic meter up here. Okay, we said all this. And then here, let's just think about this a bit. So we know that's the rate of reaction. And from this, we can see that two molecules of A are combining to give us B. That means every time one molecule of B forms, two molecules of A are disappearing. So that means the rate at which A disappears is twice as fast as the rate at which B is formed. And this is how we can write that, right? The rate at which A disappears, right? And note the minus sign here. That's a deliberate minus sign. So this is, we read this as the rate of consumption of component A. So the rate at which A is consumed is twice the rate at which B is formed. So by default, R itself, Ri, is the rate of formation, and then minus R is the rate of consumption. So rate of A is twice rate of B, and this is a common error. Well, this is correct, but many students make the error of putting the A on the wrong side, because of course when you write the chemical reaction, the 2 looks like it belongs next to the A, so the tendency is to write the 2 there. So you have to think about this, right? Twice A is disappearing, so the rate of A disappearing is twice the rate of B forming, so the 2 belongs there. And so by that logic, we can generalize this and say, if we have any chemical reaction, we can write that reaction as the rate of any component I divided by its own stoichiometric coefficient. That will equal the rate of any other component divided by its stoichiometric coefficient. And here, the stoichiometric coefficient for a reactant by default is a minus. So this is a -2. And the stoichiometric coefficient here for a product is plus. So this is a +1. So in this case, if we wanted to write RA over nu A equals RB over nu B, then we would write this as RA over -2 equals RB over 1. Right, so that's if we use that generalized form, it looks like that. And then if you multiply both sides here, then you get this form that we expect, that minus RA equals 2RB. So we didn't really need to do all this for this simple case, but for more complex cases, that's a useful relationship. So you can play around with all combinations of A, B, and C in this reaction and check that that this relationship makes sense and it's giving you the expected sort of a thing. Right, so that's reaction rate and reaction equations. Of course, the other important thing is that in all rates, your mass must be preserved. In all reactions, your mass is preserved. So if you are taking 3 moles of A and 2 moles of B, then the total mass there, whether it's 1 microgram or whether it's 50,000 tons, that must equal the mass that you convert that to. So you can talk about overall masses, but that also then dictates the molar masses behind these. So if component C or let's say component A had a molar mass of 1 and component B had a molar mass of 1, so that's 5. So that necessarily means the molar mass of C is 2.5 kilograms per mole. So the mass must strictly be preserved, and that puts certain constraints on what the molar masses can possibly be. Okay, so that's very basic. All this is probably high school chemistry. But anyway, let's now talk a bit more about the reaction rate versus the reaction speed. So to understand the rate of the reaction, in a way, it's useful to separate that into the speed of the event and the frequency of the event. So if you think about an event occurring, it may be, for example, if you imagine maybe the time taken by the average person to complete a Rubik's Cube, right? So maybe it takes you 10 minutes to complete a Rubik's Cube. And let's say you have 50 people working away at their Rubik's Cubes. Now, you can think of a kind of silly process where you want to produce completed Rubik's Cubes. And so you put people into a room and you tell them, okay, give me completed Rubik's Cubes. So it's taking the average person 10 minutes to complete a Rubik's Cube, and you've got 50 people there. And so you're getting 50 Rubik's Cubes, completed Rubik's Cubes per 10 minutes. So 50 completed cubes per 10 minutes, that's the rate. So the speed here, 10 minutes, that's different from the rate, 50 Rubik's Cubes per 10 minutes. Right, so that's how you can think of this. So Rubik's Cube, it's not a bad analogy, if I say so myself. In the reaction occurring, all the little atomic rearrangements and the breaking of bonds and the reforming of bonds, not so dissimilar to the making of a completed Rubik's Cube. So there's a certain rate at which you can convert to a completed Rubik's Cube. And then it also depends on how many such events are happening, how many Rubik's Cube completion events are occurring in the space. And you may imagine that maybe in the space that there are some regions where people are under duress. So maybe we apply a high temperature at one end of the room, and we tell the people there, you're not allowed out of this zone until you complete your Rubik's Cube. So with that extra motivation, the person in that part of the room might complete the Rubik's Cube in less than 10 minutes, and so on. So there are variations. The speed, the intrinsic speed, if you like, the speed happening of the event itself might be different in different regions.
I need your consent on it.
Sorry about that. So you might have different intrinsic speeds due to different environmental conditions. That's typical in a reactor. The slight changes in temperature across the reactor profile may cause slight differences in the local reaction rate, and then the frequency of all these reactions occurring, the number of such events occurring, that also influences then the overall impact or the overall outcome. So the final production rate that we see, the 50 Rubik's Cubes per 10 minutes, that's a function of both those together. So that's what I'm trying to explain here, that when we talk about speed, we might be thinking about molecular rearrangements and so on, but a rate is not a speed. It's about the frequency, or the period of the event, but it's also about how many of those events are occurring. So if you can make this distinction clearly, it helps a great deal with some of the more complex aspects of understanding chemical reaction engineering. All right. Now, in a way, this is quite neatly summarized for us. Right? The reaction rate, as we'll see many times in the future, the reaction rate is a strong function of temperature, and it's a function of concentration. And if you like, this temperature then reflects the intrinsic rate. This temperature strongly influences the intrinsic rate of reaction, the rate at which the actual atomic rearrangements occur. So the temperature strongly influences that, and then the concentration strongly influences how many such events are going to happen. And those two together make up the events that happen that lead us to an observed reaction rate. So that's the nice term for this, not from myself. So it's the nice terminology established in the field. That's the observed reaction rate. So when all these factors come together, we then observe some reaction rate, right? And this is written in the abstract. Quite often we'll get a reaction rate written in a form like this. So all this wonderful complexity we've talked about in temperature, that's just dumped into some single parameter k, and we just call it the reaction rate constant. So there's so much behind that, but we just say okay, and that's our rate constant. And it's not so constant. The temperature, it's a very strong function of temperature and so on. But anyway, that's k. And then the function of concentration, the influence on through hydrodynamics and so on, that's shown here. And so this is the concentration of component A, C sub capital A. And then there may exist also some coefficient here. So it's Ca to the power little a. And we'll talk about elementary reactions just now. So little a is the order of the reaction. So this might be Ca squared or something else, and so on. So that's that part. And then K, the reaction rate constant, that we know follows the Arrhenius type expression. So in the Arrhenius expression, you have the so-called pre-exponential factor, and there's your exponential factor, and you've got your activation energy up here. So that's how you determine K, and again, you can refer to the kinetic theory of gases to see how to work with that. Yeah, so that's the typical form for your reaction rate. Reaction stoichiometry must always be known. Yep. Okay. Here's a simple example. Sulfur dioxide reacting with oxygen gives you, so two sulfur dioxides reacting with oxygen give you two sulfur trioxides. So you can abstract this representation a bit. You can say 2A plus B gives you 2C. And if we follow the general formula that we introduced earlier, Ri over nu I equals Rj over nu j, then we can rewrite it like this. So the rate of A reacting, rate of formation of A divided by -2 equals rate of B over -1 equals rate of C over 1. So anyway, that's there. Yep, and then we'll talk about this just now, about the reaction being elementary. But we can say that the rate of disappearance of sulfur dioxide is equal to the concentration of sulfur dioxide squared times the concentration of oxygen. So this is a possible rate equation. So we need rate expression. Sorry, I said rate equation, rate expression, right? So we need a way to find a number for this rate. So this is not just a concept. We want to know we have a reaction rate of 50 moles per second per cubic meter or whatever it is. And we need a way to calculate this number. So we know we can calculate K because we introduced it here. So the kinetic rate constant, we can look up for a given reaction. We can look up the factors A and EA. We can specify a temperature, and then this is nothing but the universal gas constant. So we can get numbers for all these parameters, and so we can calculate a number for K. So we can get K, and then of course concentration, there's that depends on the operation of that reactor. So for now we can just say if we go ahead and measure the concentration in the reactor, we'll have concentrations here, and then we can work out this as a number. So all that together we can get a number for this reaction rate here. Okay, And in terms of this specific proposal, right, this is a very specific form, and on the face of it, there's no reason for us to suppose that this is the correct form that helps us predict this reaction rate. And there are a couple of rules that we can access towards finding a nice expression. So again, going back to collision theory, you will have seen in your chemistry courses that the correct way to estimate the reaction rate is by taking the product of each of the species on the reactant side raised to the stoichiometric coefficient, so the product of all those groups multiplied with the kinetic rate constant. So from collision theory, if you go back and revise your collision theory, you'll see why this is. And this applies only to elementary reactions. By elementary reactions, we mean that when we say that this is the reaction, we are saying that this is exactly what happens, that one or two molecules of A combine with one molecule of B, and they give us two molecules of C. That's the smallest set of steps we can come up with. We are saying that there isn't any subdivision of these steps possible. We are not talking about SO2 complexing with component D, and then component D is attacked by O2, and then it forms some other complex, and then some kind of D derivative desorbs, and then we've got SO3. So we are saying only these species are involved. We can't subdivide this reaction any further, and so this is what we call an elementary reaction. There's nothing simpler, right? So elementary reaction, it's as the name implies. There's no simpler way to express this reaction step. So if we know this is an elementary reaction, then we are allowed to use this approach to figure out the form of the rate expression that we need. So of course, this is not the only possibility. Not everything is an elementary reaction. We might easily write a reaction equation like this, and there will be many hidden sub-steps that we didn't know about. So those would be non-elementary reactions, and those reactions do not follow this expression, and we will need to do other kinds of work to figure out the rate expression. But for elementary reactions, yes, we can do this. Okay. And then there's some terminology we can apply if it's unimolecular. So if you've got one molecule of A just breaking down to give us some products, then that's, of course, if this is an elementary reaction, then that's Ca to the power 1, so kCa. If it's two molecules of A giving us products, then the order is 2. So again, the stoichiometric coefficient applies here. And so on. So if it's bimolecular, then it's CaCb, right? So that's what we can do with elementary reactions. Our reaction might also be reversible. So if A and B combine and it gives us 2 of C, so you get individually C molecules going off. But what if 2 C molecules come back together? So if 2 C molecules collide, then there's a certain chance that they will reverse their operations and give us back A and B. So reversible reactions, and generally speaking, everything is reversible. It's just that sometimes the reverse reaction is much slower than the forward reaction. And people tend to say, oh, it's not reversible. Well, everything is reversible, but it's just that sometimes the reverse rate might be so low that we treat it as if it doesn't even happen. So if all these reactions are elementary, so if the forward reaction and the reverse reaction are both elementary reactions, then clearly the rate of the forward reaction is K1 CaCb, and the rate of the reverse reaction is K1 Cc squared, and this is K1 minus to signify reverse reaction. So K1 minus Cc squared is the rate of the reverse reaction. And here we are saying that that forward reaction minus the reverse reaction, that's going to be the net rate of consumption of component A. So clearly A is consumed in the forward reaction, and then we gain A in the reverse reaction. So we lose A in the forward reaction and we gain A in the reverse reaction. And then we write that, if we write that in terms of consumption of A, then we are losing A, so it's a positive loss, if you like, of A, and then a negative loss, which is a gain in the reverse reaction. So reactions can be reversible, and we'll come back to that later. Now, if it's reversible, then it's possible to reach some equilibrium amount of each of these. So if we imagine that we start with only A and only B, let's say we start with 10 moles of A and 10 moles of B, then we are not at equilibrium. Then the tendency is that system is going to run away and start producing C straight away. But we can imagine as, let's say, 10 moles of A and 10 moles of B combine and give us more C. So let's say 5 moles of A and 5 moles of B get consumed. That leaves us with 10 moles of C here, right? So we are left with 5, 5, and now we've got 10. And let's say at this level of 5, 5, and 10, we reach equilibrium. In other words, the 10 moles being converted back to A and B is balanced by the 5 and 5 being converted over to C. So even if 5 and 5 combine and give and try to form one more mole of C, by then the 10 moles of C will also have converted back to A and B. So you can get the cycling between C, A, and B, but they can reach a point where they are at equilibrium. And equilibrium is a special state. It's a state, when I say special state, I mean it's a specific set of numbers. So there are specific concentrations of A, B, and C that will be at equilibrium. So in this made-up example, I'm saying at 5, 5, and 10, we are at equilibrium. Then that also implies that, let's say it was 3, 3, and 6, or rather, if 3 and 3 are converted, then that's actually 7, 7, and 6. Then that's not at equilibrium. You can go. There will still be a tendency for A and B, for the forward reaction to be faster, and for this to be slower. So these two rates don't always have to be the same, right? So when you are not at equilibrium, then one of these rates will be higher than the other. So A and B going forward might be faster than C going backwards. But as more A and B get converted to C, the leftover amounts of A and B will go down. And that means this term gets smaller overall. And then as you convert more A and B to C, then this term goes up. And so this term gets bigger. So this term, it started out that this term was some value and this term was 0. But as time goes on and these amounts go down, this term gets smaller and smaller, and this term is getting bigger and bigger. And it will reach a stage where both these terms are equal. And when that happens, the net amount is a 0. And so the system is in a state of balance, if you like. So that's what we call the reaction equilibrium. And at this reaction equilibrium, we have the special state where the net RA is 0. And we can say those two rates are equal. And we can use a subscript little e to signify that that's the equilibrium state now. So that's the special state of equilibrium. And we can also we can say that, well, if that's true, if at equilibrium RA equals 0, then we can equate these two terms. So 0 there, take one term across, you can equate them and say those are special numbers. And then you can rearrange this. You can say K1 plus divided by K1 minus, and then take this thing across to that side. That's equal to CC, and I should say CE, AE, BE. So it's equal to that. So at equilibrium, we can find a relationship among these concentrations. Okay, so that's the concept of equilibrium. And then another concept is conversion. It's more of a definition. It's not really a new concept. We can define the conversion of a component A. So if we imagine component A in some reactor, we start out with a certain initial amount of A, and then as time goes on and A gets converted, then currently at some time t, so let's write this in terms of time. So we can imagine we started with an initial amount of A, and then A was being converted, and then if we look at the reactor now, we only have NA of NA at the current time t. So then we just define NA minus NA naught minus NA over NA naught. That's the conversion. So for example, if we started out with 10 moles of A, and we now have 3 moles, so 10 minus 3 is 7, then 7 divided by the initial 10, so that's 0.7. So we can say the conversion is 7, or 0.7. So 70% of A has been converted. So that's the concept of conversion. And then if the volume is the same initially as at the current time, then we could just divide everything by V. So dividing top and bottom by V, we can recognize this is the concentration of A initially, so Ca naught, and this is the concentration of A at the current time t, Ca, and then down here is the concentration initially as well, so this should be a Ca naught. Right, so that's conversion. And so we can rewrite all our concentrations in terms of conversion like this. So returning to the example of A plus B goes to 2C, we can say if A is converted by an amount XA, then we have Ca remaining, so Ca equals Ca naught times 1 minus XA. And then if we have equal amounts of A and B in the reactor initially, then Cb naught equals Ca naught. And then if 1 mole of B is converted along with 1 mole of A, so then the same conversion applies. So 1 minus Xa times Ca naught is the same as Cb. And then we are producing twice as much C as A is converted. So the amount of A that's actually converted is Ca naught times X. So twice that is the amount of C that's formed. And so if we go back to our equilibrium, right, we said equilibrium was this arrangement of A, B, and C. And so if we substitute these relationships with conversion in here, you can see the Ca naughts are going to cancel, leaving us with this relationship only. And this is nice because now we've gotten rid of all those components, and now we've written this totally in terms of conversion only. And that's a function of K. So K being the ratio of K1 plus and K1 minus. Okay, so that's what we can do for conversion. And again, this is all high school chemistry. In a way, this is all just a revision session. And from our thermodynamics, we can find a relationship between the equilibrium constant, and this is the same K1 plus over K1 minus. So the relationship between the equilibrium constant and the Gibbs free energy is this. And you can refer to your thermodynamics course in second year to see why this is. So we have this nice relationship. That means we can look up in thermodynamics tables this value Gibbs free energy. We can just divide by the universal gas constant and the current temperature, and then we can calculate K. And so that means if we know the temperature in the reactor, we can go ahead and find this number K. And once we know this, it's a simple matter to go and solve for XAE. So look how easy this is now. It's telling us that if we know the temperature, we automatically can calculate the conversion. So the equilibrium conversion. So we'll be able to say, if I apply a temperature of, say, 500 Kelvin, I can then tell you what the equilibrium conversion will be. Maybe it's 40%. So I know the tendency of the system is towards 40% conversion. And that is telling me how nature is going to behave. It's telling me if I'm applying 500 Kelvin, nature is going to want to go towards a level of 40% conversion. And so then I can design my reactor around that. I know this reaction wants to go to 40% conversion, so that's not good enough. I need to raise my temperature or something like that. So this is part of what we try to do in reaction engineering. We try to understand the tendency of nature to behave. We understand the constraints by nature. We understand that nature respects the material and energy balances. And nature it tends to fall into specific levels of operation. And once we know this, once we can quantify this, once we know what equilibrium nature is trying to go towards, then we can build a reactor around that. We can say, well, I know that nature wants to go to 40% equilibrium. So it's pointless me going and making this tube 50 meters long. I know that we're going to reach 40% around here, so maybe it's only 10 centimeters. So my reactor only needs to be 10 centimeters, and I've reached my equilibrium limit. I can't do any better than that. And so either I'm going to redesign this and use a higher temperature or something else. But under these operating parameters, this is the constraint nature is going to impose on me. And so my design needs to change in response. So that's all we are trying to do in this course, right? This is all just a long introduction to say, we build these things that look like they have a lot of control over everything. But behind it all are the laws of nature, which we have to design our way around. We have to know how to navigate nature and construct a space in which we can, in a way, exploit nature and be able to develop our production targets and deliver a production rate and a purity, and we'll be able to do that if we know enough, if we have studied the thermodynamics of the system, if we know enough about the kinetics, if we know how to account for all the complications behind the reaction rate. So that's the introduction to this course. This is what we'll be doing in the coming weeks.